Okay, so let me just finish the lecture yesterday. So it was a little bit rushed. At the very end, I was showing you some numerics. I was showing you some numerics, but I never really explained how I got them. Also, Jamir yesterday was talking about phase space methods. Also, Sebastian has been teaching you about path integrals. So I wanted to finish yesterday's lecture by give you at least some very broad overview of how this phase space method works. They are actually very intuitive, very simple, but they are very powerful when you want to do dynamics out of equilibrium, in particular if you want to do large-scale dynamics. So let me give you a little bit the intuition of how this method works. And then I will refer you to some good review articles. So let me do a depiction of my phase space. And let's assume that I start from let's start with bosons first. So let's assume I start from some initial state. Let's assume it's something simple, some product state. And probably from Sebastian's lectures, you learn how to write a path integral for bosons. Let me use where let's assume in general, let's take a generic Hamiltonian, where it could be they may have nonlinearity, so we express a path integral in terms of classical variables. And probably you already know that if I want to extremize the action appearing in the exponents, what you will get is the classical equations of motion. For bosons. So let's assume that I put in a computer the classical equations of motion and I solve them. And so what I will get is some trajectories along a line. This would be the classical evolution. So far we didn't include quantum effects, but as you know, these are quantum degrees of freedom. There are fluctuations on top of the classical path. And one way in which you can, in principle, include those fluctuations, let's see if I have a different color, is to assume, for example, that as you are doing your classical simulations on your computer, in some steps you do some, let's say, random quantum jumps, which are governed by canonical commutation of bosonic degrees of freedom, which essentially amounts to assuming that you have fluctuations of the fields, which is order 1. So imagine now you start adding quantum jumps and you will get a slightly distorted classical trajectory. And let's assume that I keep repeating this over and over again. I start sampling over all possible trajectories with quantum jumps. And at the end of the day, for example, if I want to compute an expectation value, let's assume you want to compute a 2-point correlation function of quantum operators, what you end up translating is into a classical expectation over all possible trajectories. So you can do it. It's some way of doing some sort of Monte Carlo sampling over all possible trajectories, and this actually works remarkably well in a lot of situations, which I will explain later. Let me make an additional comment. Usually, if the Hamiltonian is nonlinear, you know that very likely this would be chaotic in a classical sense. So one simplification that you can do in numerics is that you really don't, if the system is really classically chaotic, adding quantum jumps in the middle of the trajectories in reality it's not buying you much. So usually the way these numerics are done is you add fluctuations on the initial condition, and this will already allow you to sample very in an ergodic way all of phase space. So the question is, when do these methods work well? When these phase space methods work well? There are, I would say, in general, two conditions. Usually they work very well if you're looking at simple observables. So in my lectures, I was always talking about, for example, two-point correlation functions of simple operators, or if you're looking at the single site expectation value. So if the operators are relatively simple, these methods work very well. So if you remember the lecture of Sarah on Monday, or the seminar, he was looking at something much more complex, so he was looking at entropy. So in that case, it probably wouldn't work nearly as well. And the second condition is when the dynamics has some sort of effective classical limit, and explicit, not necessarily will be explicit, so you may not know how that classical limit works, but if there's an emergent classical limit, these methods actually work pretty well. This is as far as boson goes. So in my lectures, I've been talking about spin systems. So although at least most of the textbooks that I know of field theory, usually they talk about bosons and fermions. But you can actually use the same arguments if you have to study, for example, a spin Hamiltonian. The key difference is that now, instead of working with bosonic coherent states, you have to work with spin coherent states, which have so a spin coherent state is locally the spins, so they are parameterized by two variables. So in bosonic case, they are parameterized by one complex variable. So you have to do a rotation. So first you do a rotation in the, okay, let me. So you essentially grab the largest state. So for example, if you have a spin 1/2, you pick the state with magnetization up, and then you do a rotation in the x-axis, and then you do a rotation in the z-axis, and this will give you a spin coherent state written in terms of two classical degrees of freedom. You can repeat all the calculations. Of course, they are a little bit even more lengthy, so I'm not going to write them, but at the end of the day, what you will write is a path integral in terms of spin coherent states. That looks like S cosine theta minus H. So the first term that appears is the very phase term, essentially is the solid angle that is covered by the spin, and the second part is the Hamiltonian. And you can do exactly the same procedure if you write the classical action of this, if you write the saddle point solution of the action, you will get the classical equations of motion for spin, which are the Landau-Lifshitz equation. And again, you do exactly the same type of procedure. You first solve the classical equations of motion, but you add fluctuations. So for example, let's assume that I start from a state that is initially in the z direction. So basically, that means that my expectation value for the z component of, let's say, spin I is S. So this essentially means that SIX equals 0. SIY is 0. And then you need to add fluctuations on the transverse direction. So basically, SIX squared So for example, you can add Gaussian fluctuations, which where this would be order S. So this relation comes from just the properties of spin, so SIX squared plus SIY squared plus SIZ squared equals S plus 1. So if you know that this one is S squared, then you will get that the typical fluctuations of the X component would be actually S over 2. So you do exactly the same procedure where you sample, for example, if you know that the spin is Sy, you add fluctuations in like Gaussian fluctuations, for example, you can add with this amplitude, and then you do the classical evolution. In the same way, you can do, again, stochastic jumps, you can add them during trajectories, or you can add them in the initial conditions, and they work. Yeah. Well, I would say variational principle seems to be much more generic. So you can grab any state in any, like you can grab an MPS state, for example, written in terms of classical variables, and then you, oh, I think it's out of battery. Yeah, I think. Okay. Do you want me to hold? Okay, I'll just hold. But going to your question, I think what you're talking is something much more generic. So here I'm already picking a representation of spins in terms of spin coherent states. I'm not, it's variational in the sense that you are extremizing the action, but then there's an additional part, which is you add fluctuations, quantum jumps along the trajectories. So, mhm. Can you repeat again how would it be? Yeah. Yeah, I think it makes sense what you are essentially saying, but what you are saying essentially would apply to anything, right? I can always write whatever state I want in whatever variables I want. Whether that's a good description of dynamics, that's a different story. But let's assume I pick one parameterization of states. Variational principle will tell you what are the right classical equation of motion of your parameters that would best reproduce for example, the Schrodinger equation. Or something like that. So that would be a much more generic. So here I already pick what my representation is. Right. No, you're right. This is I already specify what's my representation, and then is it good representation or not? That's when you should question the validity. And what I'm arguing is that if the dynamics has some emergent semi-classical limit, usually it works well. Particularly if you are trying to describe simple operators. If you want to describe something more complex, probably you shouldn't be using this type of approaches. Right, when you write, this is already classical, right? So this is written in terms of theta and phi, or if you want, you can write into a block sphere, a vector. So this is a classical vector. Right, so This is purely classical, right? So essentially what you're doing is you are, when you initialize the state, so you already know what's the expectation value. So in this case, I picked, for example, polarization in direction C. And this would give you the evolution without fluctuations if you forget about this, right? So this would give you one trajectory. But once I say, okay, now the system is quantum, I want to incorporate quantum fluctuations, I would modify the spin. Instead of pointing in the Z direction, maybe it will be pointing in the Z direction plus some Gaussian fluctuation of order S/2. And that will kind of move the spin a little bit. And then you re-evolve the system, of course, because this is chaotic. The trajectories would look very different. So you're sampling kind of ergodically the classical phase space manifold with, let's say, a typical size of given by quantum fluctuations. Yeah. Yeah, of course. So if you, for example, if you are interested in computing Si at time t and Sj time t0, you evolve the trajectory, you compute the spin at time t, you compute the spin then at time t0. When you do all the averaging, you average overall classical configuration. Yeah. No? It's the same. I call it phase space method more generally, but it's truncated Wigner, where essentially it's more formal. So here I wrote this. What does this mean? Here I said Gaussian fluctuations. In reality, you have to sample with a Wigner function. Yeah. Truncated. This is exactly truncated Wigner. Right. So in truncated Wigner, you have to be more careful how you sample. Particularly when you go to the smallest limit, you have to use a Wigner function. Yeah. So it's very common. There are various ways of doing the sampling. For example, at least in my own research, I usually use Gaussian sampling, but then there are other works. So let me actually add the references. So there's a very nice review article by Polkovnikov. This, I think it's 20, which is called phase space methods of phase space representation of quantum dynamics. I think it's 2010. There's also a different way of doing the sampling, which is a paper in the group of Anna Maria Ray, which is more a discrete type of sampling. I think it's a PRX. I don't remember who was the first author, but Anna Maria is there. I think it's a PRX of maybe 2015, if I recall correctly. But effectively, all the methods are doing semi-classical evolution plus some sort of way of how to incorporate fluctuations along the trajectories. No, you can keep. Mm-hmm. In the largest limit, it converges to a Gaussian function. So if S is very large, yes, you will also see that the Wigner function looks Gaussian-like. So then if you are working in largest limit, then it's a Gaussian. If you work in the smallest limit, it's not a Gaussian, but you can still use a Gaussian to leading order. Again, if the intermediate, if there's some emergent classical degrees of freedom, probably won't matter, because the details of how you initialize the system, it won't really change too much. Okay, yeah. That's a great question. Yeah. Right. That's good. That's a great question. So when you add these fluctuations, you are not preserving the norm. But it turns out that it usually averages out. So there's no there's no problem regarding this non-conservation of norm. So what he's asking, these classical spins, usually you preserve, it's order one, they are vectors of magnitude 1, but here I'm actually changing a little bit the magnitude of the vector. Usually that's a great question, usually it doesn't really matter. This thing about that these fluctuations are much smaller than the amplitude of the spin, particularly in the largest limit, usually it averages out. So, yeah, and the second question? Yeah. Well, let's assume you want to compute the quantum correlation. So what you are doing, what I argue that you can do is you compute the classical correlation and you sampling over, so here it's averaging over all classical configurations obtained after sampling. So this is, so that you would assume, so it should approximate very well the quantum scenario. Yeah. Yeah? Okay. 2 more questions, yes. No, I don't know what would happen. I never.
Generally, like from a technical point of view, you don't care about. But if S is small, like, could it be?
If S is small?
If S is small, like fluctuations would have a larger impact over the norm and this issue. And so, like, I mean, I would sample and then normalize the vector so that the length is still.
No, you don't have to normalize. Usually, you know, that's as I was saying, it's a good question. In general, you don't have to. But again, it is also related to the fact of when this method is valid. So for example, if you want to describe let's say a spin liquid, you are studying spins in some sort of a more complex lattice where there's frustration, and you know that the system is, there's entanglement and correlations are encoded very non-locally, then probably this is not going to give you too much information, this semi-classical approach. It works well when, for example, if in the cases I was discussing yesterday, for example, where there is a tendency to ordering or there's fluctuations of some sort of order parameter which are relevant, in that case, you would argue that if there's some sort of collective excitations where you are averaging over many spins, so the fact that your local spin is quantum, but you're averaging over many, so you effectively get some sort of effective semi-classical description. So again, you always have to ask yourself, is this the right method for the specific problem you are asking?
But also from a more fundamental point of view, like of the method itself, because you started saying that we have these jumps along like the classical trajectory that we are trying to take into account and upon sampling the initial state. Mm-hmm. But like I'm aware that truncated Wigner approximations does not take care of jumps. Like
no, you could if you wanted to.
I mean, it's like additional order, I mean, it's beyond this, or am I wrong?
Well, it depends. If you want to be completely rigorous and formal, you could potentially design the method to add them. Practically, at least most people I know of, they don't do that. Just because if you are studying something which is already chaotic in a classical sense, then why does it really matter if you add fluctuations in the middle of the path? Because you're already exploring ergodically phase space. So the simplest way is just to add fluctuations in the initial condition. But you could perfectly do it in between.
But if, for instance, the classical Hamiltonian, underlying Hamiltonian is integrable?
Which one?
The underlying classical Hamiltonian is integrable. For instance, Richardson-Gaudin magnet. Like it's an all-to-all model where you have disorder on the splitting of spins.
Well, so if you have all-to-all, I would say it's probably even more valid to use truncated Wigner, because usually in those cases, you have a giant spin, so it probably behaves even more classical than...
But you have some source of inhomogeneity that allows you not to have... You don't have permutation invariance, but still the model is integrable. Like, I mean, in case you have an integrable model, should you be worried about using this method?
You are talking integrable in the quantum.
In the classical
Hamiltonian.
Yeah, like the underlying classical.
That's a good. I never thought about it. Probably yes, you should worry. I never thought about it. At least all the cases I know are systems which are explicitly chaotic in the classical sense.
Okay.
Yeah.
Thank you.
I think there was one more question. Oh, you're good. Okay. Okay, good. Okay, so this was more as general background. You know, if you are more interested in learning, these are very good papers to learn the method. They are very intuitive, very simple, so I thought it wouldn't hurt just to spend a couple of minutes explaining them. So now let's switch topics and let's go to the last topic of my lecture, which is what I will be talking is about hydrodynamics. Of fractons. Let's see. Let me give you let's start very broadly. So what have we discussed so far in the last two lectures? So essentially what the picture I showed you is that one way in which universality or something emergent can arise in some prethermal regime is, for example, if I initialize my system in a highly excited state, and as the system wants to approach, again, this is my artistic impression of phase space, as the system wants to approach the thermal state, maybe it will get stuck somewhere, some interesting fixed point, which is not necessarily a thermal state. And during a long-lived prethermal regime, the system will inherit all the universal properties of this point rather than the thermal state. And we discuss various mechanisms while this can happen. We discuss, for example, an ordering field could prevent thermalization, or we discuss also how the distribution of charges, for example, energy and particle number, can constrain how a system relaxes, and then you will get into some interesting power loss described by turbulence and so on. What I want to discuss today is something slightly the opposite regime. What I will ask is, let's assume that I have a many-body system. So it's an interacting system, and I start the system from something that I would believe is a thermal state. So I would believe it's a system at rest with a little bit of fluctuations, thermal fluctuations, or a little bit of noise. And I would ask whether there's a chance that for whatever reason, interactions would drive the system to something very different, to some non-trivial fixed point, which has interesting dynamical scaling, which are not the dynamical scaling that you would predict from usual thermodynamic assumptions. So the motivation, okay, so why would one care about asking these questions? Well, there's one example that is widespread and it appears in various contexts, which is the KPZ universality class. Goes for Kardar. What is he? Which it appears in many models, in general one-dimensional models. So for example, let me give you an example. Let's assume I'm doing hydrodynamics and I write a fluid in one dimension. So I write Navier-Stokes equation in one dimension. And then I have a viscous term. And you would, let's assume you start from a situation where the fluid is static, so it basically velocity is zero, or the velocity field is very small, and I add a little bit of noise, or I add some sort of drive, which somehow describes thermal fluctuations in the system. What you would naively think is that any kind of inhomogeneity will relax diffusively into the system, so you will get some sort of diffusion. But what ends up happening is that in 1D, fluctuations are very strong. And this nonlinearity will turn out to be relevant, and you will get non-trivial dynamical scaling exponents, like the Z3/2. And these type of situations are very common. It appears in surface growth, it appears in transport of edge states of metals, and it's very ubiquitous. And one may wonder whether this is the, okay, this is probably, I would say, it's the most common interaction-driven universality class. And the second motivation is that in the last few years, there has been a lot of work on fractons. I will explain what fractons are in a bit, which kind of share similar properties to conventional fluids, but they have their own features of their own. It's a new phase of matter. And essentially, the question that I will be addressing is that if I want to derive, for example, a hydrodynamic equation of fractons, whether they would have some interesting physics. So we can take it as an academic exercise, but at the end of the day, we will find that fractons can actually realize similar physics to KPZ, but also they have their own unique features. So to start setting the stage, the first thing I need to do is to explain hydrodynamics, or how to derive hydrodynamic equations. I'm not sure how many of you are familiar with hydrodynamics. Okay, so let me just start by saying that hydrodynamics is basically the most universal theory you can write of a many-body system, of the dynamics of a many-body system, that as it approaches equilibration, that only includes the minimal ingredients, which are the symmetries of the system. So think that you have a system which is at very large temperature, so there's no symmetry breaking, there's no order parameter, and so on. And you ask the very simple question of, okay, what are the most generic equations I can write that describe the approach to equilibration of a system in those conditions? Let's see. Maybe we can start here. So again, the key ingredients are, so we have a system that I will assume spatial locality, and the only other ingredient is a system that has symmetries. So the key idea of hydrodynamics is, let's assume that this is my system, this is now real space. So this is X and Y. The key assumption that you do in hydrodynamics is to assume that the system reaches a state of local equilibrium. So that essentially means that if I'm observing my many-body system, and I zoom in into a region that I will call I will refer it as the thermalization length. And I measure all kind of observables within this thermalization length. And what I will see is a Gibbs distribution. So for example, let's assume that my system has only energy conservation. So what I would observe is that in this local region, there would be, let's say, a temperature describing my Gibbs ensemble. But the key feature is that this temperature, maybe if I look at a different region, this temperature would be different. So there would be local equilibrium, but there won't be a global equilibrium. And then the question that one can ask is, okay, given that you have local equilibrium everywhere, but no global equilibrium, how does the system as a whole will approach thermodynamic equilibrium? So for example, if you had more conserved charges, so for example, if you had I don't know, particle number conservation, you would have an additional term in the local Gibbs ensemble, so you would have a chemical potential, which will also be position dependent. This is the number operator, and if you had, for example, momentum conservation, you will have an additional potential, would be your drift velocity. So these are all the chemical potential of your of your conserved charges. So far, so good. So then, yeah. It's an assumption, right? So Well, you can, well, if you have let's say you have a classical system, let's assume you are doing some sort of molecular dynamics type of simulation where you zoom in into a region, and into a small region, and you compute what's the distribution of particles, right? So if your region is very small, maybe you will see that it doesn't look like a classical distribution, like a Boltzmann distribution, and then you start going larger, larger, larger until you find the characteristic scale in which the distribution actually looks thermal.
I see. So then it's just like I kind of coarse grain the thing,
yeah.
And then like I see if it follows like Gibbs distribution, and then the point is that at different points it will follow Gibbs distribution with different temperatures
exactly.
and other parameters. Okay,
correct.
Perfect,
that would be, so think about that. What I'm doing here is I'm dividing my system into blocks of a correlation of thermalization length. I'm coarse graining my theory. I'm forgetting about all the information. So in principle, the distribution could have a lot of information about position, distribution of momentum. I just throw everything away and I put the distribution only in terms of the chemical potentials, temperature, chemical potential for particles and drift velocities. So now you transform a very challenging problem of determining the full distribution function to something that has only 3 degrees, or if you have only energy, you would have only 1 degree of freedom, or in this case, you would have 3 degrees, well, 5 depending on dimensions of velocity, or 6, I don't know, depending how many physical dimensions you have. So you transform a problem, a complicated problem, into a simpler one where you now need to write, again, classical equations for how the temperature, how the chemical potential, and how velocities. So now the second step is, what are these equations, right? How these equations evolve to reach equilibrium, yeah.
For quantum systems, is this the same as assuming the eigenstate thermalization hypothesis? Because you're assuming that.
No, well, eigenstate, no, not really, because, right. So you're assuming that, for example, the density matrix looks like a Gibbs ensemble, but the Gibbs ensemble here can be very different from the Gibbs ensemble here, right? So it's a kind of a different statement. It's just assuming that locally you have a equilibration.
Okay, thanks.
So deriving those coefficients, like
which coefficients?
So for instance, like well, okay, maybe I should more say like, so given the microscopics of the system, right? Like trying to figure out like how would like temperature vary at say like a certain intermediate time scale, and like what are some some constants related to it. Like that would be at the goal of like some kind of like microscopic simulations, and we're not there yet. Like we don't know how to derive the.
Correct. That's okay. So for example, let's assume I have a microscopic theory. Let's assume we go back to the class. Let's assume I have something kinetic theory, for example. So I have a system which is weakly coupled particles. So with kinetic theory, you can actually do calculations analytically and compute. Basically, what you're asking is, can you compute the transport coefficients of hydrodynamic theories? And you can do it. But kinetic theory is very limited because it assumes that there's a weak coupling limit in your theory. What is very powerful of hydrodynamics is that even if you have a strongly interacting system where there's no weak coupling limit, hydrodynamics still holds. In that sense, it's the most universal theory you can write. You don't really need a microscopic model. You can write the most generic equations here at the cost of not knowing what are the transport coefficients. So if it's a strongly coupled theory, it would be very hard to get transport coefficients. But otherwise, if there's a clear weak coupling limit, you can do analytics in that case. And going back to your question, the approach I will use here is very general arguments of what would be the right equations that I have to write here without assuming any microscopic theory. So I would be much broader in that sense.
But like, would you sort of require from like the underlying microscopic Hamiltonian or something to eventually thermalize? Like it's related to the
yes, you're
question.
assuming chaos, right? So
Okay.
it's the most universal theory you can write of a many-body chaotic system.
Okay, perfect.
Integrability, okay, now that you mention it. If you had integrability, actually there are ways you can write a generalized Gibbs ensembles.
Okay.
So these objects would look actually much more complicated. But here I'm talking about systems where there are a few conservation laws, so it's a smaller set of symmetries, but the system is chaotic. So that's crucial. But again, integrable systems are more like fine-tuned points, so this actually should be very broad and very generic.
Perfect, thanks.
Yeah. Okay, so let's start to set the stage. Let's start solving a couple of simple hydrodynamic examples. Let's assume. Okay, let's assume that I have only one charge, which could be, for example, a particle number. So the example would be, for example, let's assume I add impurities in a lattice, and so let's assume I have a system with impurities in a bigger crystal, and these impurities can move, but because they are interacting with the lattice particles, they don't preserve either energy or momentum. So the only conserved charge is the number of impurities that I have in my system. So then the question you may ask is, what's the most universal theory that you can write that describes the motion of these impurities as they approach thermalization? So usually the arguments that you do, it goes in two steps. First is continuity. So you know that the impurity number is conserved. So essentially, if I look into a small region, the amount of, I will call n as the number of impurities in some region within the thermal length, plus the divergence, or let me just write it as a vector. So essentially, the divergence of the current of impurities is essentially the number of impurities that are leaving a region of site psi. And this is the number, the change in number of impurities. So this equation must hold exactly. Doesn't matter about anything about microscopics. If you have charge conservation, this must hold true regardless. And then the question is, you need a constitutive relation. Which essentially tells you how currents, so currents is a vector that has, for example, has d components where d is the dimension of space. So you may ask, what's the most generic expression for current that you can write? So this has one index, and you have a scalar charge. So the simplest equation you can write is a gradient of n. So you cannot have a constant term because this is a vector, this is a scalar. So the simplest model you can write for current is just the gradient of n. And if I plug it into this expression, what you will find is nothing else than the diffusion equation. So again, if you have a system that has only one scalar charge, the most general thing that you can, the most universal way that system will approach equilibrium is through diffusive modes. An important thing that I will comment that will arise, so here, if you look at the relation between spatial variables and time variables, at the dimension of the diffusion equation, you will get a 2. Or I define this as, in my previous lecture, I defined this as beta, as the relation between spatial and temporal variables. So in general, if you were to look at two-point correlation functions, what you will see is a power law tail with exponent 1/2. So diffusion is kind of the most general equation that describes a system with a single scalar charge. Yeah.
Sorry, this constitutive hypothesis, I didn't understand this step that the current is given by
Well,
this.
J is a vector, right?
Yes.
So the question is, if you have to write a vector that tells you how charge would flow in terms of, let's say, densities in nearing sites or in nearing regions. So what would be the simplest, so you have to do a gradient expansion, right? So the question is, what's the simplest gradient that will show up? Remember also I'm assuming locality here, so each region is talking to its neighboring. So the simplest equation you can write is just a gradient.
But is it possible to have more complex stuff? Because here, I mean,
I will
gradient,
go there in a bit.
Okay.
Yeah.
Okay.
So in principle, unless there's a symmetry that prevents you from having a gradient, you could have higher order. So I could, well, maybe I could just keep going, right? I could write D2 second. So this would, in principle, like a Laplacian. No, sorry. I could have, for example, well, I could have, for example, a Laplacian of n, d alpha, and so on. So I could start building higher order gradients, but these are usually less relevant because think about it, that here what I want to do is a theory that is true at longer and longer scales. So I'm coarse graining the theory, so usually these terms will be less relevant than the first term. So unless there's a symmetry that prevents you from having this term, you will get diffusion.
Then a question in general, but here, like in the long time, let's assume, I'm trying to anticipate, I don't know if it is actually.
So this is the script of long times, right?
Okay, no, but like I would expect that you would have a uniform temperature and all over the system, like that. I mean, the regions where there is a well-defined temperature and this constant increases in time, I suppose, something like that. I don't know.
So you're thinking about
equilibration. And I was wondering, I mean, going to the question raised before, like, do you have that this is the same answer that you would have from, for instance, against-state thermalization hypothesis? Because I don't know, is there here quantum?
No, hydrodynamics is, again, it's a classical theory of, so hydrodynamics applies so if you have a quantum theory that is chaotic, this would be a coarse grain. So if you want to coarse grain the theory, so you are taking more and more degrees of freedom into account, you will get an emergent classical theory that the only things that matter, this is also encoded in the Gibbs ensemble, are the chemical potentials of the system. So this perfectly applies to a quantum. Doesn't matter if you have an exotic quantum theory but so long as it has locality and it has symmetries and you are considering the infinite temperature state. So there's no, here I'm not including any, you could if you wanted to, but I'm not including it. You could have, for instance, some ordering or something like that, but let's forget about that. If you only have symmetries, this is the most generic thing you can write. And people have seen this, for example, there are lots of papers of simulating this with quantum circuits where you only preserve one charge, and you will see that at very long times you will get diffusive scaling. So this is very generic. Classical or quantum, right? Yeah. If you, sorry, can you repeat? Like if you want to write a hydrodynamic theory of domain walls. Yeah, so long as the system is thermalizing, that there are, let's say, if you're thinking about the classical theory, so long as there's interaction, yes, it should work fine. So you would have to worry, for instance, if domain walls are freely moving and they are free particles, so the system is integrable. In that case, everything breaks down. But so long as there's some sort of nonlinearity that allows you to reach thermodynamic equilibrium, then it should work generically. So if instead of particle number I have energy as my only conserved charge, you would also get diffusion of energy rather than particles. So this is very generic. Yeah, this formalism can be used in any case. Any case, so long, again, the key word here is you need to reach thermalization. And there's also a locality, right, the spatial locality. So in that case, it will always apply. In that sense, I started the lecture saying this is the most universal theory you can write of any many-body system, of any chaotic many-body system that describes the approach to equilibration.
But there are exceptions to this, because, I mean, otherwise it means, there is, as far as I know, a lot of research ongoing, also looking for systems that, although are chaotic, they don't thermalize. And so we'll expect that there is a breakdown of this thing.
For example, that would be a little bit contradictory.
Like, for instance, I mean, they do eventually maybe a very, very long time, so that, for instance, kinetically constrained models there are models where you have...
That's what I will discuss in a bit. But they still, you can still think of them as thermalizing.
but they're different from fractons, because there is no... Like, fractons, there is Hilbert space shattering that is preventing you to, like, as far as I know, that is kind of... But instead, in this kind of model, it's more similar to glass, that you have full access to the whole Hilbert space. So technically, you will expect thermalization, but still, this does not occur.
No, I will discuss that case.
Okay.
I will discuss that case, and you can apply the same tools of hydrodynamics. So you are talking about like dipole conserving systems?
Sorry?
Like systems with dipole conserving?
Are a different class, but we can
Okay,
talk,
we can talk about later.
I mean,
but I will go there in a bit.
Thank you.
Again, so usually, as I was saying, if you compute the two-point correlation functions or of a many-body system, it's very common that you will find diffusive scaling. Let me do one more example. I don't know, how am I on time? Okay. So let me add one layer of complexity. So let's assume that now, in addition to charge, I also have momentum conservation. So how would you write the hydrodynamic equations of a system that has both a scalar charge, like particle number, and momentum? So, well, you have to apply exactly the same approach. Because the two charges are conserved, you write a continuity equation for charge, which is exactly the same. Let me just write it in terms of sub-indices. So it's the divergence of current. This is the current of charge, and then there would be an equivalent expression for momentum, or let me write it in terms of velocity. Where now I have a stress tensor, which essentially has two components, because I have d components for velocity, and then I have a current which tells you in which direction this component is flowing into. So again, I have two constitutive relations for charge and momentum conservation, and then I need to write the constitutive relations that, for example, it turns out that now I don't need to go to gradient expansions. The leading order component would be velocity. So in fact, very generally, you can show that if your system has Galilean symmetry, this is probably a technical detail, the leading order component would be already the velocity, because now this already has a vectorial form. You could, of course, still write a gradient of n if you wanted to. But you don't have to go to gradient expansion. You already have one term which is vectorial, and then I can do the same thing for the pressure tensor or the momentum tensor. So now I have two components. So this is a tensor. What is the most generic form that you can write for this object? There could be one term which is diagonal. This, in standard hydrodynamics, this is just pressure. This is local, so this is the same pressure that you would compute using statistical mechanics at equilibrium. Then I have, I could write, for example, V alpha, V beta. What else could I write? I could potentially write d alpha n, d beta n, and you can keep writing any gradient expansion that you like. And of course, if you plug it in here, you will get, well, if you assume, for example, that the system is incompressible, you will get Navier-Stokes equation if you plug it in this term in the continuity equation of momentum. But let me just make one clarifying point. Let's assume that pressure which usually is true, pressure is proportional to the density, so this is a number. The simplest model you can write for pressure is proportional to n. And let's assume that I do linearize all the theory, so I assume that velocities are small, so I can discard this quadratic term, and you write the linearized hydrodynamics, what you will find. So you will have dTn plus d alpha b alpha, and then I will have dTv you will have a gradient of the pressure, which would be the n. So if you solve this linearized equation, what you will find is that you will find modes that instead of being diffusive, there would be ballistic modes. So essentially, this is what's called a sound wave. So you can have, when you have both momentum conservation and particle number conservation. Now the mode, instead of being ballistic, is diffusive. And if you look at correlation functions, you will find a ballistic, you will find a linear relation between spatial and temporal variables. So if I write Z, in this case, it's what I call before 1 over beta, this would be 1. So this is another conventional mode that appears in hydrodynamics, which is a ballistic mode. So usually you have either ballistic or diffusive modes. I would say 99% of all many-body theories, at the end of the day, you get with something which is either ballistic or diffusive. That's very generic. So in the end, anything that is different from 1 or 2, it's kind of non-trivial and interesting in its own right. Of course, ballistic and diffusive can still be interesting, but in general, if you get Z or a dynamical exponent which is different from 1 and 2, you know that you are observing potentially something very interesting. And as I explained at the beginning of my talk, the canonical example would be if I do hydrodynamics of an incompressible fluid in 1 dimension, you will get the KPC equation. So actually not the KPC, you will get Navier-Stokes in 1 dimension, which you can map it to the usual KPC equation, and that will give you a Z equals 3/2. So in that case, you have something which is non-trivial. That would be the canonical example of a non-equilibrium, of a different universality class, which is not, which has no diffusive or ballistic modes. So far, so good? Yeah. This one? This one?
Yes. Yeah.
So I started by saying I will linearize the equation in terms of a equilibrium state. So I said B to be very tiny, so I discard this term. I discard this gradient, so I have pressure is proportional to usually density. So if you grab a usual fluid, so then the gradient of pressure, so this is diagonal. So usually the change in momentum is the gradient of pressure. So this is the usual term. And this is linear in N, this is linear in B. You solve this equation, you get just linear dispersion of ballistic modes. So you get sound modes. Okay. Okay, so now let's go to something more non-trivial. Well, let me also mention that, so as I mentioned, the KPC universality class is probably one of the most generic and appears in various different contexts. So there are various ways in which you can break this usual expectation of 1 or 2. And in the last couple of years, just for general context, there has been a lot of work of studying integrability, integrable systems. So in those cases, you have, if you wanted to write a hydrodynamic equations, you would have to write a very long list of extensive number of conserved quantities. And they also found in those cases that you can have non-trivial scaling. Let me show you. Right, so in the last probably 5-6 years, if you try to write generalized hydrodynamics, what is interesting, you still get KPC universality class, but it's slightly different because in this case you have integrability. Let me see if I can, is a pointer? Yeah, can you see the pointer? Yeah. In this case, what they are studying is exactly the model we have been discussing yesterday, but in 1 dimension, which is the Heisenberg model with nearest neighbor interactions. And if you, in particular, when you put delta equals to 1, so you're at the isotropic point, and you look at spin-spin correlation functions, you will see that there's a growth, let's say, there's a spatial relation. The spatial and temporal variables are related by the KPC scaling exponents, which is kind of interesting. This is actually a purely quantum model, so it's kind of interesting and kind of unexpected that you would find some sort of some scaling associated to a classical universality class, but in the last couple of years, you will see that there was a lot of work on integrable models. But in this case, again, you cannot use, slightly different is because you have a much longer list of conservation laws. But still you have KPZ. So the model that I wanted to discuss, and now I will introduce it, is a model which has kinematic constraints. And what I will try to do is repeat this type of the same exercise of writing what would be the most generic hydrodynamic equation and see whether we find something interesting. And hopefully I will answer some of the questions that I got asked a few minutes ago regarding the constraints, dipole constraints. So let's do a simple model where I will use the same type of line of thought. So let's assume that I have a system that has charge conservation, right? So I know that if I integrate my charge density over the entire system, this would be a conserved quantity. And let's assume that I add a second conservation law, which I would call it the dipole constraint. The dipole moment, which I also assume is conserved. Let's think about the case in one dimension. So let's assume I have a charge. Let's assume that my system is very dilute number of charges. And let's assume I have a charge at site I, and this charge decides to move to the right. So in this process, of course, charge is conserved, but you will see that dipole moment is not. So the moment this charge wants to move to the right, it will increase the total dipole moment of the system. That's not allowed by symmetry. This process is not allowed. A charge cannot move anywhere by itself. So if you have a local charge in the middle of the system and there's nothing else, the charge is essentially immobile. But now let's assume that there's a different scenario where at site I have a positive charge, and nearby I have a negative charge. So now, of course, each of these charges cannot move on its own, but let's assume that the two, let's say they group together, and they move to the right or to the left. Now, because you have a positive and a negative charge, dipole moment does not change at all. So in this sense, this is kind of a simplified version of fractonic models where single excitations cannot move by themselves, but they can move in tandem if they group together with another excitation. Yeah.
So perhaps just a quick question on like the previous stuff as well. So when we have this continuity thing, then like I'll get one equation for every conserved quantity.
Yep.
So this is kind of like how does the microscopic Hamiltonian come in, like except for transport coefficients. It's just that I need to look at the symmetry, so it's going to preserve.
Yeah.
Okay, and then okay, great, and then like within this.
Actually, that's not entirely true, but keep finishing the. I will give a counter example.
Okay, so then another thing is like within this dipole moment, like can I allow to, for instance, like swap plus with a minus, or that
like
thing
change the
orientation?
No.
Okay.
No.
So
So you have positive and negative charge independently from each other. Let me give you a counter example of what you just said. So let's assume that you have commuting charges. So if you have non-commuting charges, then it's fine. You can write the potential for each charge. But if you have commuting charges, then it's not true that you write the Gibbs ensemble in terms of all charges because, for example, let's take the spin system we discussed yesterday. You have SU2 symmetry. Usually, you don't write the charges in terms of 3 vectors because there could be a total magnetization in one direction. You write the chemical potential for the C component, and the other ones are fluctuating. So there's no chemical potential for X and Y, or if you want, you set them to 0. But the fact that you have non-commuting charges kind of puts a constraint on what goes into your Gibbs ensemble, and here it would be the same. Actually, this has actually a lot of similarities to what we discussed yesterday in terms of spin systems, because these are not independent charges, and I will go to your point in a minute.
Perfect, thanks.
Actually, let's go to your point now. So let's assume I want to write local equilibrium. The naive thing you would write is a Gibbs ensemble which has a chemical potential for this charge, and you will have another potential. Let's call it nu alpha d alpha. So this would be your naive guess. But I will argue that this is not true. That in reality, what dipole moment is doing is not really adding an additional charge, but is constraining. What you would get for the effective equations of motion of n. And the calculation is relatively simple. Let's assume I take time derivative of d alpha, dt of d alpha. So this would be integral of dx, x alpha, dt n. So now I can use the continuity equation for n. So this would be d beta j beta. Now I can take the derivative out. So I will get minus. So of course the total derivative, because this is a total integral, will not contribute. So I will get delta alpha beta j beta, or minus dx j alpha. So and this, because I said that this dipole moment is conserved, this has to be 0. So the integral of the current over all space has to be 0. So the only way that can be true is if my particle current can be written as a total gradient of something else. So I could write it as, for example, alpha, beta. I don't remember which notation I was using for this one. I'm using K. Right? So it's again, so if this is 0, the only way this can be 0 if this is a total derivative, and I will call this current alpha beta. You can interpret it as a sort of dipole current. And now I can go to the constitutive relation of n and write dn, dtn, plus d alpha j alpha. And this would be dtn plus d alpha d beta k alpha beta equals 0. So now you see that higher order derivative would start appearing, and this goes to the first question I was asked before. In this case, a symmetry, which is dipole symmetry, is constraining the number of derivatives that I can allow in my current. And I can ask the question, okay, what's the most generic form that I can write for k alpha beta? Now I'm left with one scalar charge, so the most generic thing I can write is the alpha n. Actually, no, let's write the linear term, so the alpha d beta of n. And now I plug it in, and I will get, let's call it d. Let's assume it's in one dimension, so I will get d to the 4th of n. So here I have two derivatives, two additional derivatives. Let's restrict to one dimension, so you will get that now, rather than having diffusive scaling, this will be sub-diffusive scaling. So this would be even slower than diffusion, where now the exponent would be 4, or 1 over beta is 4. And it's not surprising that it's lower than diffusion because you have an additional constraint. So you are not allowing charges to move freely. You are only allowing charges to move when they group together. So it's not surprising that it's actually slower than diffusion. So far, so good? Yeah. So hydrodynamics is a theory that describes a coarse-grained theory, and it describes approach to equilibration. So it's usually a long-time dynamics. So usually what the thing about that the starting point is to assume local equilibrium. So there has to be, the system needs to evolve sufficient amount of time such that this local equilibrium sets. But once it sets, then you're good to derive hydrodynamics. So it would describe the late-time dynamics of any many-body system, chaotic many-body system. Yeah.
One question.
Yeah.
About the dipole moment. The reason why it does not appear in the thermal ansatz that we can do is because it's not a local conserved quantity. Could be seen as a reason because it is an intro over the x of x times n. So it looks to me that it's not local. This is the reason?
I don't know what you mean. No, well, it is local, right? In what sense?
I don't know if can it be written as the sum of terms that are acting locally? It doesn't look to me immediate.
Well, think about it that it's adding a local constraint on motion of charges, right? So this won't do much if charges are. So effectively, it will manifest it locally. So I don't. Well, it depends what you call local in this sense. So if I have a positive charge here, and it's isolated, then.
What I call local is like I look at the conserved quantity, and it looks to me that it cannot be written as the sum of terms that have a finite support in the thermodynamic limit. It looks to me that you have to integrate from 0 to the system size. So you have the x alpha, and this x makes it essentially.
Maybe I'm not understanding the question, but okay. But wouldn't it be, for example, in total spin? So, for example, if I have a spin system with SU2 symmetry, wouldn't you write it as a sum of all local terms?
Because in the case it's a sum of local. Is there like the usual debate about the generalized Gibbs ensemble? Should I keep track also of global conserved quantities or just the local conserved quantities there? And it looks to me that this falls into this case that essentially you don't have to keep into account in the thermal ansatz that you're doing this conserved quantity because it's not local. And I wanted to know if...
so I'm not familiar, what's the debate in the Gibbs ensemble? So in the Gibbs...
Because like any system you could define, for instance, non-local conserved quantities that has
like the
projector over the eigenstates.
Yes.
And the thing is that, okay, we don't put them in the Gibbs
Okay,
generalized ansatz because are global conserved quantities. And I was wondering if here is the same.
I'm not sure. Yeah, maybe we can discuss it later. I haven't thought about it in those terms.
Also, if I may, it's not clear to me, KF alpha beta, why this ansatz of partial derivative alpha and beta. Sorry, I lost it. If you could repeat.
Why this is
yes.
Well, you have now you have a dipole current, which is a tensor with two components. And now you have one scalar charge, right? So if you believe that dipole moment should not be considered as an independent charge because they are related to particle number, then I ask you what's the most general tensor you can write. It's the same argument that I did, right? So it's a derivative, the alpha, the beta, and then you get a subdiffusive scaling. Yep. The diagonal part. No, right, that would imply isotropy of the right. Yeah, let me think about that one. That is actually a good question. No, okay, there has to be a reason why it's excluded by symmetry, but it doesn't come to mind now why. Okay, so far this is good. So now one can do the way, actually, actually, we did it. It's more like an academic exercise, is we can ask the question, okay, what happens if in addition to charge and dipole moment, I also add momentum? So if I want to generalize this equation and write an additional conserved quantity, so essentially what I would get, just for the same arguments, I will get the alpha d beta, k alpha beta equals 0. So I assume that there's charge conservation, and now in principle I could write an equation of motion for momentum. Good. Right, and we can ask, okay, so we can ask exactly the same question of what would be the general form of pi alpha beta, but again, constrained to the fact of having dipole moment conservation. And of course, one needs to write the most general theory. It's a little bit cumbersome to go through all the details, but let me just give you some intuition. In a normal fluid, you would have that momentum is directly related to the drift velocity of the system. So naively, what you would write for the Gibbs ensemble is an entropy term that depends on density and P alpha. But from the intuitive picture that, and I'm not sure if this is related to your question, the intuitive picture that you have is that the total mass or the center of mass of all charges is not moving. So the system cannot, so if you compute where the center of mass is, just by this constraint, you cannot move it, which effectively means that the mass that you would get here would be infinity. So the leading order relation between velocity and momentum should come for very similar reasons that you would have for charge. You will have the higher order gradient. And the simplest gradient you can write would be a Laplacian. So these two have already subindices. So the leading, so now drift velocity is written in terms of gradient, and you wouldn't have a constant term here. You would have to write entropy in terms of gradients of momentum. So again, this is a more technical side, but the key idea is that now entropy is no longer a function of momentum, so you wouldn't add a chemical potential associated to momentum, but you would have to build a more complicated object where you have gradients of momentum, and you will have a chemical potential which has alpha and beta components. Again, I don't have too much time left, but essentially this will constrain the form of the pressure tensor. So you will still have a diagonal term, alpha, beta. Let me remind. And the only thing you have to believe, I don't have time to explain, is that here you would have, rather than having a second order derivatives, you will have a cubic derivatives. So you will have, let me write it as a Laplacian of the alpha p beta. And this current is exactly the same as I wrote before. Again, so the only distinction with the normal fluid is that you will get also higher order derivatives of the allowed terms of the pressure tensor in terms of momentum. And now I can ask the question of that I asked for the fluid at the beginning of class. Let's assume I want to linearize hydrodynamics. So I want to find what's the linear behavior of a system that has both charge and momentum. So here pressure, I would assume there's nothing that prevents pressure from being linear to n. And you can also add quadratic terms and so on. So if you linearize the hydrodynamic equation, the only thing that you would find, which is different, is that now the modes are no longer linearly dispersing, but are more like a Magnon sound mode, so they are quadratic dispersion. So you have an additional gradient of momentum. You still have the subdiffusion, but now you will see that modes, instead of being ballistic, it's quadratic. It's more like a Magnon-like type of excitation. But then you can ask a second order question is, let's assume that now I move away from my linearized hydrodynamics, and I start including the leading order nonlinearities into the theory. And what I can ask is there anything interesting about nonlinearities, or are nonlinearities relevant in the same sense that a KPZ equation, were in the same sense as in the case of KPZ that I discussed before. So let me just simplify the key ingredients. If I focus only on the equation of motion for pressure, what you will get to leading order is a subdiffusive term. So you will get the gradient of pressure. Let's focus on one dimension. So let's remove subindices. So you will get a term which is quartic on gradient of pressure, which will give to the diffusive pole. And then you may ask, what's the leading order nonlinearity in the system that is allowed by symmetry in the pressure equation? So you will see that the leading order nonlinearity is a pressure term. So I could, in principle, write n plus n squared. So the leading order nonlinearity here would be gradient of n squared. And in principle, I can keep going. If you write the full, actually, let me just add the reference. So the paper where all the details are discussed. It's Glorioso, Guo, myself, and Lucas. This was a Nature Physics of 22 last year. So there you can find all the terms, but let me just focus on the relevant, on the important terms for my discussion. So you have that the equation of motion for momentum. They will have a subdiffusive scaling, so d to the fourth. Again, this is due to dipole constraint, and the leading order term would be a gradient of n squared. And you may ask, in the same sense that you would do, and let me compare this with what would be KPC equation, or Navier-Stokes equation in one dimension. So you would get dp plus diffusor. So now you can see that there are different gradients that are allowed by symmetry, and then you would naively expect that this is already will lead to non-trivial scaling exponents. So let me do a quick type of scaling analysis. So let's assume I do some RG, where I coarse grain my theory and I look what happens at longer and longer scales. Around the Gaussian fixed point. So let's assume that my n variable will scale so this is a Gaussian, so this would be 1 over square root of dimension. So this would be psi d2 over 2. So let me call k is 1 over psi, so this would be d over 2. And I will scale momentum. The only thing that you have to keep in mind is that when you write entropy and momentum, there's an extra gradient here. So this would scale, so dp would scale as 1 over psi d over 2. And then you have an extra gradient, so this would be minus 1. So this would scale as k d minus 2 over 2. And I ask in which conditions or in which dimension. So basically the question I'm asking is, when I coarse grain the theory, in which dimension would this term be more important than this term in the limit of psi going to infinity or in the limit of k going to 0, right? So if I plug in this scaling, let me just do it here. So for dp, d4 to the p, so here I will get k d over 4 plus 3. And the nonlinear term is n gradient of n. So here I would have k to the d plus 1. So in the limit of k going to 0, you would ask when is this term dominant over this one? And you will find that the condition that needs to be met is d over 4 plus 3 is larger than d plus 1, which essentially means that d is less than 4. So probably this is kind of the key result of this work, is that when you allow, so there are two key distinctions with KPZ. First of all, you have higher order derivatives, and then there's also the difference scaling of entropy with momentum, which is written in terms of gradient. But once you include those two effects, what you will find is that nonlinearities in the hydrodynamic fluid are relevant in dimensions larger than 4. And this is, at least to the best of my knowledge, the only case where you can have some sort of non-trivial scaling in physical dimensions of 3. So usually you need so usually most common cases, of course, in 1 dimensions where you have where fluctuations are very strong, but in this case, even in d equals 4, you can see some non-trivial scaling. And you can ask the question now, what's the dynamical scaling exponent? So what would be how omega will scale with k when you do the coarse graining, and you will find that that z in this case would be d over 2 plus 2. This is 1 over beta. So for example, in 1 dimensions, you will have 5 halves. And in 2 dimensions, you will have a 3. And you can, sorry, in 2 dimensions, you will have 3. And in 3, you will have 3 halves plus 2. Again, let me show you some I don't know, how am I on time? Am I good? Okay, let me do just one more. Okay, the key message that you have to take is that in this case, nonlinearities in this fluid, it would be that nonlinearities are relevant in dimensions less than 4. And here what I can show you is a simple model. Actually, I added, there should be a problem set in the website that I wrote. One can write a very simple model that has both, that has charge, dipole moment, and momentum conservation, which is essentially a type of lattice model where B is a generic polynomial of the difference. So X is the position of particle I, P is the momentum of particle I. The only non-trivial thing is that here the quadratic component, rather than being proportional to Pi, is proportional to the difference of Pi. And the problem set, you will have to show that you have 3 conservation laws, that the 3 charges that I discussed are preserved. And usually, and what we showed, for example, if you do numerics, and again, here what we are doing, essentially is we are doing some sort of initialization where we start from a fluid at rest, so there's no net momentum. The system is almost, you would think, as a thermal equilibrium. And there are small initial fluctuations, so there's no drive. And what you will see is that as you start evolving the system, you will start building correlations, and you will start seeing that correlations will start evolving towards lower and lower momenta. And by how this peak moves in momentum space is how we find the scaling exponents, the value of C. So this is in 1 dimension, so we are rescaling the momentum correlation functions with 5 halves, and you see that almost perfect collapse. And of course, in the paper, you can also find numerics for higher dimensional systems for a 2-dimensional model, and you will also see that this very cheap scaling analysis that I did here works actually remarkably well. Of course, we don't have we don't have an analytical proof that these scalings are the correct ones, but already in this simple way of doing scaling, everything works remarkably well. With this, I just want to finish because I'm already 5 minutes over time.
Okay. But yeah, thank you very much, Nieva. We still have time for questions, I would say.
Yeah. Oh, that's a great question. Good. So this model, if I don't add any noise, we add energy conservation. We would have to add an additional equations for energy conservation. So usually energy conservation does not couple to the other modes. And we assume that in the work. So in the work, we also added noise in some numerics, just to show that there's no qualitative change in numerics. And so our belief is that energy is not coupling to the basic equations that I wrote. The noise? But you wouldn't see it even in some prethermal regime, that even... I see. I see. No, but I mean, even if you start from a fluid at rest where you add fluctuations in the initial condition, you wouldn't see any kind of scaling in that case. Yeah. Oh, sure. Yeah, okay, sure. Yes. No, what I'm thinking is you start from something at rest, but not that everything is zero, is you add some sort of fluctuations in the initial condition. But in that case, you think it would be the same, right? You would get KPZ. Yeah. So, but in these numerics, we added noise in the initial conditions. So we added.
Questions? Okay, we are a bit out of time also, so I would say thank you again, Nieva, and we can go for the coffee break.